Hello and welcome back to your Chem 4 lecture. We are moving into chapter 10 today, and we're talking about acids and bases and the equilibrium that forms between them. So acids and bases, of course, we've used them in lab already, but as it turns out, acid and base properties are extremely important for understanding biological functions. Your body can only tolerate a very narrow range of acids in the blood, let's say, or base in the blood. And there's all sorts of mechanisms set up to make sure that your blood and your saliva, your stomach acid, of course, is at the right acid level, or what we call pH, which we'll follow up here by the end of the chapter. So acids and bases, as it turns out, are extremely important for all sorts of reasons that we're going to talk about in this chapter. Okay, so we're going to start by defining them. First off, the term acid comes from a Latin word, which is acidus, which means sour. You may be familiar with the taste of vinegar, like in a vinaigrette, for example, or lemons. The reason for that is because these foods contain acids. Vinegar contains acetic acid, lemons contain citric acid. So what does that mean, actually? Well, we have a few different definitions of acids that we're going to explore. First, we're going to talk about Arrhenius acids. Then we'll talk about Bronsted-Lowry acids. And the way you can think about it is basically just different sets of definitions, depending on what you're following along. So starting from Arrhenius acids. These are the most commonly referred to acids in common nomenclature. This is when we think of acids, we think of things like hydrochloric acid, for example. And you can identify an Arrhenius acid because an Arrhenius acid will produce hydrogen ions when it's dissolved in water. So if you take hydrogen chloride gas, bubble it through water, the hydrogen chloride separates out into hydrogen ions, these what we call protons, and chloride ions. Now I want to emphasize that again. I'm going to periodically be calling these hydrogen ions protons because, as you know, hydrogen being the first element has one proton in its nucleus, one electron that it comes with. If it loses that electron, it has a positive charge, and that means that all that's left over is a proton. So just so you know, we will be calling these protons as well. Now, these are electrolytes because when they're in water, they've fully dissociated to hydrogen ions and chloride ions. These have a sour taste, and they will turn blue litmus red. Litmus paper is one of the most common types of chemical tests that basically detects base or acid. It's where the word litmus test comes from. Litmus test literally tests for acid or base of a certain liquid. And these Arrhenius acids will be able to corrode some metals. Okay, so here now we're finally going to talk about acid nomenclature. I know I maybe mentioned this earlier. Sometimes it's paired with ionic nomenclature, but in this book we have a separate chapter for acids. So now we're going to talk about how to name acids. So if you have an acid that has a hydrogen ion and a nonmetal or cyanide ion, then the way that we name those is having a prefix called hydro and ending with ic acid, in addition to the root of the word. So for example, HCl, it's acid of chlorine, right? Cl is chlorine. The root of chlorine is ClCHlOr, or chlor. So we add hydro to the front, hydro, then the root, chlor, and then finally ended with ic acid, so hydrochloric acid. The other thing that happens here for cyanide, if you have HCN, that becomes hydrocyanic acid. I don't know if that'll come up, but it may show up at one point or another. So yeah, hydrochloric acid. Now, that's just if you have basically a binary acid like HF or HI, H3N, for example. Now, you can also have acids with a polyatomic ion, and it's really actually pretty easy. Once you identify the polyatomic ion that is attached to the proton, then it's a very simple substitution in the name. So for example, if you have chlorate and you add a hydrogen to it, so you get HClO3, that's our balanced acid compound. All of these acids have an H there. What you do is the 8 becomes ic acid. So chlorate as an acid, HClO3 becomes chloric acid. Ite, on the other hand, changes to OUS acid, or US acid. So ClO2 minus is chlorite, and make the acid HClO2, that is chlorous acid. So I know that's a lot to process, but it's a pretty straightforward process if you can just identify the anion or nonmetal that is the acid hydrogen ion is paired with. So yeah, here's a table of it. Again, you don't have to memorize this. It's just kind of provided for you here, so you can kind of go through it. For example, nitrate, NO3 minus, when it's turned into an acid with hydrogen ion, becomes HNO3. That's known as nitric acid. How about sulfuric acid? Well, ic acid, that tells us that it's an 8 ion. So from sulfate, which is SO4 2 minus. So to balance it out, we have to have 2 hydrogen ions. We form H2SO4. Okay, so why don't we go ahead and give a correct name for each of these? So I don't know if I provided the list there in the PDF or not, but we have HBr, we have H2CO3, and HBrO2. Why don't you go ahead, pause the video, and try to pick out the correct name for each of these acids. So go ahead, pause. Okay, and we're back. So HBr, the anion is bromide. So it's just a single nonmetal ion. So you know that you have to put hydro in front and ic acid at the end. So hydroic acid and with a brom in the middle. So hydrobromic acid. H2CO3, that's the acid of carbonate, CO3 2 minus. You see the 8, drop the 8, add the ic acid, it becomes carbonic acid. Finally, HBrO2, we have BrO2 minus as our anion, bromite. When we form an acid with a proton, that becomes bromous acid. Remember, ite turns to us, and 8 turns to ic. Okay, now how about bases? Well, bases in the Arrhenius definition are basically anything that dissolves to produce hydroxide ions in water. These will have a bitter flavor or sometimes a chalky flavor. So if you've ever had Tums, for example, Tums usually has some, it could be like calcium hydroxide, magnesium hydroxide. That flavor is, I mean, it's usually disguised by something, right? Like it's either minty or fruity or something like that. But that is an example of a base that you may come into contact with. These are also electrolytes because you have ions in solution. Sodium hydroxide, really good example, dissolves in water, dissociates into sodium ions and hydroxide ions, which of course are ions dissolved in water, allow it to carry a current. The feel is soapy or slippery. Don't necessarily go looking for it because, of course, a concentrated enough base will be, will burn you. But at the right concentration, you can feel it as a soapiness. And then finally, litmus indicator turns blue, and as you'll discover in lab this week, phenolphthalein turns pink. Okay, now fortunately, these are just named as hydroxides. So there's sodium hydroxide, potassium hydroxide, barium hydroxide, aluminum hydroxide. Nothing different from the ionic nomenclature we've actually already learned. Okay, so why don't we go ahead and match up the formulas with the names for sample exercise 2. We have the acids and bases here. We want to match it up with the correct name. So go ahead, pause the video, come up with your answers, and then we'll look at it together. So pause. Okay, and we're back. So the matching is basically HNO2 is nitrous acid. CaOH2, that's calcium hydroxide. H2SO4 is sulfuric acid. HiO3 is the acid of iodate, so iodic acid. And then finally, NaOH is sodium hydroxide. Okay, so there you go. The acids produce hydrogen ions and the bases produce hydroxide ions in water. And then you can kind of compare the different properties here. Okay, so here we are. We're ready to kind of identify here in sample exercise 3, which of these are characteristics of acids or bases or both. So go ahead, pause the video here, try to identify the correct characteristics of acid or base, and we'll look at the answer here when we finish up. So go ahead, pause. Okay, we're back. So 1, sour taste, that matches acid, right? Think citric acid, citrus fruits, sour. Okay, how about produces hydroxide ions in aqueous solutions? The hydroxide ions are basic, so that's B, basic. Chalkiness, that's a basic flavor. and is an electrolyte. Both of them, Arrhenius acids and bases, are electrolytes. And then finally, produces hydrogen ions in solution. That's an acid. Okay, so that's the first set of definitions, the Arrhenius acid and bases. The next set is the Bronsted-Lowry acids and bases. And this basically focuses on a different part. Whereas with the Arrhenius ions, we were focusing on, the production of which type of ion in an aqueous solution. With Bronsted-Lowry theory, what we're going to do is look at the reactants of a problem and identify which one donates a proton and which one accepts a proton. So that's what we're going to kind of check out here with Bronsted-Lowry definition. Okay, so let's look at NH3. And we're going to tell you straight up, NH3 is a Bronsted-Lowry base. Okay, so when you put ammonia, NH3, in water, it reacts with water by pulling a proton off of the water and forming the ammonium ion. Now, after a proton's been removed from a water molecule, you're left with OH minus, or the hydroxide ion. So what happens is the base accepts a proton, the base ammonia accepts a proton from acid water. And that is our definition. I guess I should have mentioned this here. An acid is a substance that donates a proton in a reaction, and a base is a substance that accepts a proton in a reaction. Okay. Yeah, okay, so there we go. All right. Ooh. Yeah, so again, you just want to identify, in identifying these acids and bases, which one accepts a proton during the reaction and which one gives up a proton during the reaction. So let's go ahead and give it a shot. So A, we have the reaction of nitric acid with water to form the hydronium ion and nitrate. So ask yourself, which one gives up a proton and which one accepts a proton between the reactants? And then finally, we have HF. HF reacts, which is hydrofluoric acid, reacts with water to produce the hydronium ion and the fluoride ion. So go ahead, pause the video here. Try to identify which is the Bronsted-Lowry acid and which is the Bronsted-Lowry base. Okay, so here, nitric acid gives up a proton to water. And you know that because you start with nitric acid and you end with nitrate. So you lost a proton. If it gave up a proton, that means it's an acid. On the other hand, you started with the water and it picked up a proton to form the hydronium ion, H3O+. So clearly water acted as the base and accepted the proton. Okay, next up, we have the acid, HF, and the base, H2O. Here, again, we see that we start with HF and we end with the fluoride ion. So clearly HF gave up a proton to form the fluoride ion. Likewise, the water molecule picks up a proton to form the hydronium ion. So HF is acting as the acid, it donates its proton, and water is acting as the base. It accepts the proton. Okay, now what you notice here is that one really helpful way of thinking about Bronsted-Lowry acids and bases is thinking about what happens to the acid at the end of the reaction. So looking at what happened to the HF, for example. You saw, okay, it was HF in the reactants, and it was F- in the products. So you're able to identify that it gave up a proton. Now, in a lot of reactions tend to be reversible. So in other words, you have a forward reaction and a reverse reaction. And this tends to happen a lot in acid-base reactions. As it turns out, you have basically the forward reaction like we looked at here, where the acid reacts with the base. The acid loses its proton and it forms the anion, whatever is left over, A-. And then the base picks up the proton and forms BH+. Okay, now flip it. Think about the reaction going in reverse. A- could react with BH+ to pick up a proton from BH+. That would form B and HA. In other words, in the reverse reaction, A- acts as the base, accepting a proton from BH+, and BH+ acts as the acid, giving up a proton to A-. Basically, you have this one reaction going the forward way, the reverse reaction goes the opposite way. So that gives us what we call acid-base pairs. HA and A- form one conjugate acid-base pair, where HA is the acid in the forward direction, and A- is its conjugate base in the reverse reaction. B is the base in the forward reaction, and then BH plus is the acid in the reverse reaction. So let's look at a specific example here. For example, HF and H2O, like what we saw in the sample exercise. Well, hydrofluoric acid donates a proton to water to form the fluoride ion and the hydronium ion. Okay, well, HF gives up a proton, that forms fluoride, and water accepts a proton to form H3O plus. Now, flip it. Imagine the reaction going in the opposite direction. Now the H3O plus can give up a proton to the fluoride ion, and in that case, it would act as an acid. So we call H3O plus the conjugate acid. So the base accepts a proton and becomes the conjugate acid. Likewise, in the reverse reaction, the fluoride would accept a proton. In other words, it would act as a base. So while HF is the acid in the forward direction, F minus is the base in the reverse direction. Okay, and you can think about it this way too, like for example, ammonia here, NH3 accepts a proton from water. So it is a base in the forward direction. And then in the reverse direction, it gives up a proton to hydroxide. And so it's the conjugate base, or I'm sorry, the conjugate acid. Likewise, water accepts the proton, or I'm sorry, gives up a proton in the forward direction. So it gives up its proton, and that means that it is acting as an acid. In the reverse direction, the hydroxide ion picks up a proton, in other words, takes in a proton from ammonium, and therefore is acting as the conjugate base. So the base in the forward direction becomes the conjugate acid in the reverse direction. And likewise, the acid in the forward direction becomes the conjugate base in the reverse direction. Okay, so let's go ahead and give it a shot. Why don't you write the conjugate base for each of the following acids and a conjugate acid from each of the following bases. We have a list there: HBr, H2S, H2CO3, and then we have nitrite, ammonia, and hydroxide. So give it a shot. Try to come up with what the conjugate base would be for each of those acids and the conjugate acid from each of the bases. Let's go ahead and pause. Okay, let's take a look at the answer here. So HBr, what you can do for finding the conjugate base of an acid is just separate it out into each of its component parts. You know that if HBr loses a proton, it'll be H plus and Br minus. Therefore, the conjugate base has to be Br minus. Likewise, H2S, when it loses one proton, it's going to form bisulfide or hydrogen sulfide, HS minus. Similarly, carbonic acid, when it gives up a proton, will form hydrogen carbonate or HCO3 with a single minus charge. Next up, for the conjugate acid of those bases, all you have to do is add a proton to each of them. So NO2 minus plus a proton becomes HNO2. NH3 with a proton becomes ammonium, NH4 plus, and then hydroxide with a proton just becomes water, H2O. Okay, now try to identify which sets of these contain conjugate acid base pairs. So if a pair is a conjugate acid base, like let's look at the first one here. We have HNO2 and NO2 minus. Could these be acid base conjugate pairs? Well, sure enough, HNO2, if it gives up a proton, is going to be nitrite, NO2 minus. So yes, this could be the acid, and this would be its conjugate base. So go ahead, pause the video, and do that reasoning for 2 through 5, and just give it a try. So pause the video. Okay, we're back. So H2CO3 and CO3 2- is not an acid-base conjugate pair because you have to give up 2 protons to get from here to here, whereas a conjugate acid-base pair should just be for a single proton transfer. HCl and ClO4-, of course, those aren't the same because you don't have perchlorate in the acid. HS- and H2S, sure enough, that is a base with its conjugate acid, just like what we were looking at here on the previous sample exercise. And then NH3 and NH4 plus similarly are a base and its conjugate acid. Okay, next up, identify the conjugate acid base pairs in the following reaction. We have nitric acid reacting with ammonia to form nitrate and ammonium. So tell me what's the conjugate acid, or what's the acid and the conjugate base, and then what's the base and its conjugate acid. Let's go ahead and pause the video. Okay, So whenever you have a problem like this, always start by identifying what's the acid and what's the base. Here we have nitric acid and ammonia. So nitric acid, it tells you right in the name, this is going to be acting as the acid. And that means that ammonia has to be acting as the base. Okay, so here. So if nitric acid is the acid, it gives up a proton. That means it forms a conjugate base pair with nitrate after it gives up its proton. On the other hand, the base, NH3, accepts the proton, so it's going to form a conjugate base pair with ammonia right there. And that's your conjugate acid base pairs. Oops, okay, hold on. Let me get rid of that annotation. Oops, clear all. There we go. Sorry about that. Okay, great. Okay, so the last thing that we want to talk about in this lecture is going to be acid and base strength. Basically, some acids are stronger by nature than others. And that's what we want to talk about here in this last part. Hydrofluoric acid, for example, only partially dissolves in water, or dissociates in water. Okay, so fortunately, we can lean back on some of our previous terms that we've learned from a last chapter, where a strong acid is a strong electrolyte. So a strong acid will completely ionize in aqueous solution. So if you take hydrogen chloride and you bubble it through water, 100% of the hydrogen chloride molecules are going to turn into, they're going to separate into ions, hydrogen ions and chloride ions. Now, on the other hand, if you take a weak acid like carbonic acid and put it in water, only some of the carbonic acid molecules are actually going to form hydrogen carbonate in solution. So this is basically a partial ionization. And the way we know that is we actually see a reversible arrow here. Seems like it didn't translate for whatever reason in PowerPoint, but this should be a reversible arrow. I think sometimes it's also drawn like this for you for now. Eventually we'll get to this down here. So this is partial ionization, which means a weak electrolyte in solution. Okay. So for a strong acid, if you take, for example, hydroiodic acid in solution, however much hydroiodic acid or hydrogen iodide you start with, 100% of it dissociates into hydrogen ions and I- ions, iodide ions. Now note here that we say that it's a hydronium ion. This is just kind of a bookkeeping thing. We see that hydrogen iodide gives up its proton to a water molecule to form the hydronium ion. I can write that out for us here. And that's just because a hydrogen ion, when it's actually in water, will be picked up by a water molecule to form kind of a network like this with H3O+. And so it's sort of a new molecule. And iodide. So you get these two things from the dissociation of HI. Now, on the other hand, so there's a bunch of weak acids as well, right? But as it turns out, there's only 6 acids that you really need to worry about as strong acids. And I put 7 of them here because there's one that's not really common, but is important to know. There's hydroiodic acid, hydrobromic acid, perchloric acid, hydrochloric acid, sulfuric acid, and nitric acid are all considered the strong acids. The hydronium ion is an acid in its own, but you don't ever have the hydronium ion by itself. It's always in a solution. So we don't really consider that, its own strong acid necessarily. Okay. Now, weak acids, on the other hand, only a few molecules will dissociate. So HF, for example, and again, we should have the reversible arrow here. I don't know why all of a sudden it stopped working, but the reversible arrow here. This HF in water will mostly stay as HF molecules. So it's like 95% HF molecules, and then 5% is dissociated into hydronium ions and fluoride ions. So the bulk of it is this undissociated material. And remember that in order for an electrolyte to be strong in solution, you have to have 100% ions. Here, since we only have like 5% ions, this would be a very weak electrolyte. So that's the other kind of way that you can help remember that. And that's basically all the other acids. So almost every acid is weak, except for the 6 strong ones that, again, you're just going to have to memorize. So I just want to say those again: hydroiodic, hydrobromic, perchloric, hydrochloric acid, sulfuric acid, and nitric acid. Okay. So again, comparing hydrochloric acid and acetic acid, which is the main ingredient of vinegar. Hydrochloric acid has 100% separated out the protons in the form of hydronium ions and the chloride ions. And acetic acid is mostly acetic acid molecules with occasional acetate ions with occasional hydronium ions. This is going to come really important when we talk about pH in the next, I think, the next lecture. Okay, so that's strong and weak acids, which is kind of difficult. Fortunately, strong and weak bases are really straightforward. Strong bases are always formed as hydroxides of groups 1A and 2A. So that's lithium hydroxide, sodium hydroxide, potassium hydroxide, barium hydroxide, strontium hydroxide, and calcium hydroxide. And the reason these are strong is just simply because they're soluble in water. They dissolve completely in water, and so you get, a complete separation of ions, and therefore you get a strong electrolyte. Now, on the other hand, if you have weak bases only partially dissolve in solution or partially dissociated in solution. So once again, because these partially dissolve or partially dissociate, you get weak electrolytes. These would include ammonia, which is written down here. Basically, only some ammonia molecules become ammonium. In other words, they're strong enough to pull off a proton from water, from ammonium and hydroxide ion. And so you only get a few ions in solution. The same thing with the salts of carbonates and phosphates. Those act as very weak bases. Okay, so let's go ahead and identify each of the following as a strong or weak acid or base. So go down the list. Is it an acid or base first? And then is it strong or weak? Pause the video, give it a shot, think it through, and then when we come back, we will have a look at the answers. So go ahead, pause. And we're back. So HBr, that's one of our strong acids. It's hydrobromic acid. Again, it's one that we'll need to memorize. Then we have HNO2. It looks like a strong acid because it looks like nitric acid. But remember, NO2 minus, that's nitrite. So that would form nitrous acid, which is a weak acid. Next up, sodium hydroxide. That's the sodium salt of the hydroxide ion. So that's a strong base. H2SO4, sulfuric acid, that's a strong acid. And then copper 2 hydroxide. It's a salt of hydroxide, so it's a base. But then it's not sodium, lithium, potassium, etc. It's got to be a weak base in solution. Okay. And then finally, using that table that we had from before, identify the stronger acid in each pair, whether that's HNO2 or H2S, HCO3 with a 1- charge, that's hydrogen carbonate or hydrobromic acid, phosphoric acid, or the hydronium. So again, for this, you'll have to go back up here. So apologies, you can use this table to go ahead and answer that question. So pause the video, and when you come back, we'll look at the answers. Pause. Okay, let's take a look. So using that table, which one's stronger? Well, the one that's higher on the table is strong. So HNO2 is stronger than H2S because it's above it on that table. Similarly, HBr, one of the strongest acids that we know of, it is the stronger acid compared to hydrogen carbonate. And then finally, phosphoric acid versus the hydronium ion. Hydronium being higher up on the table is the stronger acid. Okay, that takes us through today's lecture. So, of course, we're only partway through the chapter, but you should be able to identify acids and bases now and be somewhat competent when we talk about the strengths of acids and bases. In the next chapter, or the next section, next lecture, we're going to look at some reactions of acids and bases and how we can use those. So until then, I will see you soon, and keep it real. Bye-bye.